In this video, we're going to look specifically at single displacement and double displacement reactions through a different lens. In that, we're going to look at the heart of what really goes on in a single and or double displacement reaction from a total ionic and a net ionic equation standpoint. So let's first of all talk about what total and net ionic equations are. So in single replacement and double displacement reactions, there are aqueous reactant ions that remain aqueous after the reaction is complete. In other words, they are not changed in any way. There's no new substance that's produced. So these specific ions that don't undergo a change are called spectator ions. And so that's a new definition for you to be familiar with. And the way that you can identify spectator ions is that you begin by writing something called a total ionic equation for a reaction. And from that total ionic, you can pick out and identify from left side to right side which ions are exactly the same before and after. And then therefore, if we remove those spectator ions from the equation, we end up with something called a net ionic equation for that particular reaction. So let's take a look at how this works. Let's begin with a single replacement reaction example. Our word equation begins with iron reacting with copper sulfate to produce iron 2 sulfate and copper. We do know for a fact that this reaction does occur because, as we've learned in this unit, the activity series of metals can predict it for us. And if you look at your activity series of metals that you put on your periodic table and copied from 165, page 165 of the textbook, you would notice that in going from the top, which has lithium, down to gold at the bottom, approximately speaking, iron is somewhere in here and copper is somewhere in here. So because iron is higher in this series than copper is, iron has the ability to bump copper out in a single replacement reaction. And so we can see that in the case of this single replacement, iron would take copper's place, copper would come out and be an element instead of an ion. So iron has to lose some electrons, and copper has to gain those electrons. So in losing its electrons, iron becomes charged. And we're told in this word equation that the charge on iron that it takes on in this case is iron 2 plus. So it now pairs up with sulfate, which is also a 2 minus ion. So they'll come together in a 1-to-1 ratio. And copper will come back out as copper solid and neutral copper, ionic copper, because it gains those electrons to become neutral. And the iron sulfate remains aqueous in solution, just like the copper, copper silver nitrate and the silver and copper nitrate examples we saw in class. Okay. Now, what we're going to do here is anywhere that we see aqueous, and this is what we're looking for right here, we see this aqueous term, we recognize that aqueous means dissolved in water and that therefore these ions can become hydrated with water and they actually can spread apart from each other and have like a little water party going on inside there. They can swim around, they have more kinetic energy. And so what we're going to do is anywhere we see aqueous, we're going to re-represent that compound as separate ions that are aqueous and medium. Otherwise, we leave everything else the same. So I'm going to leave iron alone because it is a solid and it's an element as a starting reactant. And then what I'm going to do is I'm going to take this compound here and split it into its positive and negative parts. So I see that I have copper 2 plus, which is aqueous swimming around in that reaction vessel, and sulfate ions swimming around in there, also in the aqueous state. And by the way, before I move on, I should note that before I began the total ionic equation, I checked to make sure everything was balanced in the chemical equation. And if you do a quick inspection, you'll see that everything is in a 1-to-1-to-1-to-1 relationship, and so no balancing was required. But I would have balanced first before moving on. Okay, on the right-hand side of the equation, I see that I have iron sulfate, and again, it's aqueous, so let's re-represent it as its positive and its negative counterparts swimming around in that water. Cool. And then we notice that copper is a solid. I'm going to leave it alone because it isn't aqueous, and so I'm just going to rewrite it as is. So the total ionic equation shows everything that's a starting material, shows everything that's a finishing material. And if you look carefully, you'll see that there's something in here that doesn't change in any way, shape, or form. If we look at the iron on the left and the right, we do see it does change. It changes charge. So that's considered part of its change. We look at copper being 2 plus over here and being neutral over here. Those aren't perfectly identical species either, but the sulfates are here before and after with absolutely no change. And so these are what are called our spectator ions. And so I'm going to remove them from the equation, not because I'm removing them from the reaction vessel, but I'm going to remove them just because they're not a part of the chemical change. They're just sitting around having a party watching the chemical reaction go on, and they're not a part of creating something new. So in turn, if I rewrite what's left over, I get what's called the net ionic equation. So I'll have solid iron reacting with copper ions to produce iron 2 ions and neutral elemental copper. And really, that's what's going on in the reaction vessel. That's the change that's taking place. Let's look at another example. Whoop, went too far. Here we go. Let's look at silver and calcium chloride. Now, the first thing I should do is make sure this reaction occurs. So if you have your activity series handy, you would see that calcium is up near the top and silver is way down near the bottom, second from the bottom. So the question becomes, can silver bump out something that's higher than it? And the answer is no, the reaction cannot occur. And so in this scenario, we would simply write, as we've practiced before, no reaction. And because there's no reaction going on, we cannot write a total ionic and we cannot write a net ionic equation. And so actually that's a really great simple scenario, but I wanted to expose it to you. Let's now look at double displacement reactions and how these total ionic and net ionic equations work. So on the left-hand side, you'll see I have lead 2 nitrate reacting with potassium iodide. And the first thing I'm going to do in a double displacement reaction is I'm going to repair up the positive and the negative partners with each other. So I can take a lead ion and I'm going to partner it up with the other anion that's in solution, which is iodide. And of course, when I do this repairing, I don't bring across any subscripts or anything. I just repartner them up, and then I see what ratio will they combine in. Well, lo and behold, we're going to end up with a 2-to-1 relationship in order to balance charge. And then I can take the other cation that's in this reaction, which is here, and it can pair up with the other anion. And notice as I clone it that I'm going to leave this 2 behind because it was there to balance charge when it was partnering with lead, but it's not partnering with lead anymore. It's going to partner up with potassium. And so let's see, when I partner it up with potassium, I look, lo and behold, they combine in a 1-to-1 ratio, and they're good. So before moving on now, after I've decided on what the products of the reaction are, let's now balance the equation. And so on the left side, I see I have a lead. On the right side, I have a lead. I have 2 nitrates, though, on the left over here. And so I can make 2 nitrates over here, not by bracketing and making a 2, because that would disrupt the charges that are balanced, but by cloning potassium nitrate instead. And then that in turn gives me 2 potassiums on the right, so I'm going to need 2 potassiums on the left. That in turn is going to give me 2 iodides, but lo and behold, I have 2 iodides on the right, and so now it's balanced. So again, first of all, let's show what the products are. Secondly, let's balance. Now before we move on, we need to know what the state of matter is for these 2 new products. And so we can use the solubility rules at the bottom of your alchem table on the ion side of it to see what happens. And so we should go across and find iodide. And you may remember on that solubility table that iodide, I believe, is right here. It's approximately halfway across as you go across the top column. And so what we want to do is find out where is lead in this particular column of the solubility rules. And I do believe you'll find that it's down here, which is in the low solubility or the insoluble area of the solubility rules table. And so what that means is that lead iodide does not dissolve very well in water. It likes to stay as a solid. And so we can put an S here. And if we do a similar analysis for nitrate, I do remember, I think off the top of my head here, that nitrate is probably around in here somewhere. And you'll see the word all under nitrate because every cation that's paired with nitrate will dissolve in water. And so because this one is soluble, we can write it as AQ. And you can appreciate from the previous slide that we need that step because we have to know whether we're going to split ions up or leave them together. So in the total ionic, I'm going to take every aqueous species and rewrite it as its positive and negative counterparts written separately. So in the first one, I'm going to write lead 2 plus aqueous. And then I'm looking at what is the negative part of that compound. What is the anion? Well, it's nitrate. So I'm going to write it down as nitrate. But how many of them are there in this case? Well, there are 2 of them. And so let's show that out front as sort of a cloning type of way. And let's write AQ here. And then similarly in this compound, my positive part is potassium, but there are 2 of them because of the way I balance the equation. And then my negative part is iodide. And again, there are 2 of them because of the way I balanced equation. So we are going to split up everything on the left-hand side because both reactants are always going to be aqueous for us in those double displacement reactions. But when we get to the right-hand side, we notice only one of the species is aqueous, the other one is solid. And because it's solid, I'm going to leave it alone. I'm going to rewrite it just as is because it actually does not exist as anions and cations floating around in solution. Those things have come together and they've fallen down to the bottom of the reaction vessel or the test tube as a solid. They're stuck together. Whereas over here, my positive part is potassium. There are 2 of them because of the balancing of the equation. And here, there are nitrates as the anion, and again, 2 of them because of the way I balanced the equation. So this time in a double displacement reaction, you're going to be able to find 2 spectator ions, whereas with single displacement, we only found 1. And when you find 2 spectator ions, one of them will be a cation, one of them will be positive, one of them will be negative. So do you see 2 things that are identical on both sides? Well, if I look at lead by itself, I see that over here, lead is not by itself. Okay, so I can't cancel it out. If I look here at 2 nitrates, I see the right-hand side also has 2 nitrates. So there's one of the spectator ions that do not change in any way, shape, or form from left side to right side. And here, if I look, I've got 2 potassiums. On the right, I have 2 potassium ions as well. So because they're in equal quantity and have not changed charge, we take them out. And upon further inspection, we see that the iodides have changed, and so we're going to leave them there. Okay, so the red crossed out ones are spectator ions. So let's then rewrite as our net ionic equation what is really going on in that reaction vessel. And what's really going on is the lead ions and the iodide ions are finding each other, and they're connecting with each other through electrostatic forces, and they're becoming a solid. Meanwhile, the nitrates are having a party in solution. The potassium's having a little party, but they don't pair up with anybody. They just continue swimming on, swimming on, swimming on, and they do not change. Let's look at one more example. What happens if a precipitate does not form, or in other words, both products are aqueous? Take a moment. I want you to predict the products of this reaction. I'm going to pause the video. You unpause when you're done, and we'll take a look and see how you did. So after being repartnered up and balanced by charge, you'll see that you end up with sodium sulfate and hydrogen carbonate on the right-hand side. And you end up with an equation that's perfectly balanced 1 to 1 to 1 to 1, which is awesome. So let's do the same process for total ionic that we did for the others. What is my positive part? It's sodium. How many of them are there in sodium carbonate? There are 2. What is my negative part? It's carbonate. How many of them? There's 1. What is my positive part? It's hydrogen. How many of them? 2. What is my negative part? Sulfate. How many? 1. Same thing on the other side. What is my positive part? It's sodium, and there are 2 of them. What is my negative part? Sulfate, and there's 1. What is my positive part? It's hydrogen, and there's 2. And what is my negative part? It's carbonate, and there's 1. So now when you start looking for spectator ions, guess what? Every single one of them cancels out. Sodiums, carbonates, hydrogens, sulfates, Because nothing paired up. There was no precipitate, no liquid, no gas made. And we often see this as no reaction. And so you cannot do a net ionic equation because no reaction occurred. No reaction occurred, as I said, because there was no gas, no liquid, which is usually water in our cases, and no solid, no funky chunky formed, and therefore no net ionic equation.